I'd like to introduce Carlos Arreche from the University of Texas at Dallas, who will be speaking on normal reflection subgroups. All right, take it away.
Thank you. Hi, good morning, everyone, and thank you for showing up to my talk. This is my first FIPSAC, and in fact, it's my first combinatorics talk ever. So when we get to the elevator talks later today, maybe I'll tell you a bit more about my day job. But Nathan gave me some advice on how to try to join your community with this talk. And let me also thank my co-author, because besides all the work that he did in our collaboration, he had the extra task of teaching me everything I know about complex reflection groups, and also trying to teach me some things about them that I don't know yet. So let me get started. Normal reflection subgroups are going to arise as special subgroups of some complex reflection groups, and I'm not going to assume that you know what they are. So please forgive me if you do know them. Okay. So in a complex vector space of dimension R, a linear transformation is going to be a reflection if it fixes a codimension 1 complex subspace and it has finite order. So if I give you a finite subgroup of GLV that is generated by reflections in this sense, that's what's going to be a complex reflection group, also called unitary reflection group in the literature. So these groups have a fascinating history and also show up all over the place. So let me point to a few of those connections. If I replace C with just the analogous definition for real vector spaces, you then get what are now called, to disambiguate, real reflection groups. And it's known that this happened to be exactly the finite Coxeter groups. And if I give you any one of these finite Coxeter groups, I can think of it as a complex reflection group by complexifying. So examples of these things are any val group of a semi-simple Lie algebra. These are the crystallographic ones, and in fact, most real reflection groups do happen to be val groups with a few exceptions, and then an infinite family of exceptions. So the study of these groups was initiated by Shephard, who introduced the notion in the early 50s, and then they were subsequently classified by Shephard and Todd, kind of generalizing the classification of val groups for semi-simple Lie algebras. And what makes them interesting for me, with my limited knowledge, is that on the one hand, these finite groups arise in a bunch of different places. So here I've written down a list of applications of complex reflection groups that I copied from the introduction to the wonderful textbook by Lehrer and Taylor called Unitary Reflection Groups. So they show up all over the place, and that makes them interesting and important to study. But the other thing is that these groups happen to have the best possible kind of invariant theory in the sense of this fundamental theorem. It says that if I give you a finite subgroup of GLV, V again, an R-dimensional complex vector space, it'll be a complex reflection group exactly when the algebra of invariant polynomials it's again a polynomial ring generated by our algebraically independent homogeneous invariants. This is one of the early results in the theory, and it also has an interesting history. So Shephard and Todd gave a case-by-case proof using their classification. In fact, it's an if and only if statement. So one direction used a classification, and the other was already case-free. And then Chevalier presented a proof of the other direction, thus completing a case-free proof of this result. But Chevalier had initially stated it only, I think, for real reflection groups, and Sarah pointed out that the arguments just worked in a lot more generality. So so now we have two different ways of characterizing complex reflection groups. First, the definition that I had in the previous slide, and now also the separate characterization. So you know, it's always useful to be able to define the same objects in two completely different ways. So the homogeneous generators for the algebra of G invariants, they are not necessarily unique, but the multi-set of their degrees is unique, and they form invariants of G. And in fact, it's known that when you multiply them out, you get the order of the complex reflection group. So a quick example of this, if you like, the symmetric group in our letters is well, real and so also complex reflection group. And as you know, there are two standard competing choices for generators of the algebra of symmetric polynomials. And well, you know, so you have two different very natural ways to choose these PIs, but their degrees are still 1 through R, and when you multiply them out, you get R factorial, which is the order of the symmetric group. So that's the kind of thing that happens in general. Another more refined sense in which the invariant theory of these groups is really nice comes from the following construction. So I can look inside of the ring of polynomial functions on V at the ideal generated by the homogeneous G invariants of a strictly positive degree. And when I take the quotient of the full polynomial ring by this homogeneous ideal, I get a graded quotient ring that's called the co-invariant algebra of G. And so you know, it's graded because it's a quotient of a graded ring by a homogeneous ideal. But there are two magical facts about it. So Chevalier proved that if you forget the grading for a moment, as a G module, this happens to be the regular representation of the group. And if you now remember the grading again, then you actually have these two decompositions of the polynomial ring as a graded G module involving this co-invariant algebra. So what this is going to allow us to do is associate to just any old G representation certain special numbers. So initially for any simple G module, say of rank M, one can write down this polynomial in Q that encodes the degrees inside of the co-invariant algebra thought of as the regular representation for the group, the degrees in which that simple module appears. And the exponents that you get at the end in this way, those are called the M exponents of G. Using this definition, the unadorned exponents of G are just going to be the V exponents where V is a regular representation. Excuse me, the reflection representation for the group. And it's known that in fact these exponents of G are related to the degrees of the fundamental invariant polynomials by just adding 1 to them. So I want to state a result that we're generalizing in our main theorem, which is due to Shephard and Todd. Again, they initially proved this following their classification in a case-by-case way, and subsequently Solomon presented a case-free proof. And if you're not familiar with an area where there's some kind of classification, then people insist on being able to find case-free proofs of the same results. Somehow what happens is that when you have a case-by-case proof of something, you've discovered what is true, but you don't know why it's true. And then a case-free proof somehow explains why what is true is indeed true. So there's this beautiful formula that relates summing over the dimension of the fixed space for elements of the group. This polynomial happens to factor into linear factors involving these exponents of the group. So this is the theorem that we generalized in the context of normal reflection subgroups, which I haven't defined yet. But let me briefly, in a small example, try to illustrate what the theorem says. So as I was preparing my slides, Nathan gave me some advice on how to give a combinatorics talk, seeing as I've never done it before. And besides suggesting that I should have at least one example, at least one theorem, at least one proof, maybe at least one joke that's not equal to the previous 3 things, he said also that at some point someone's probably going to ask at the end, what about type B? Which hopefully means something to you all. But so here's a very small example where you can see everything that's going on, and it happens to be in type B. So there, check, check, and check. So let's look at the dihedral group of order 8. It's generated by these 2 standard reflections, and here's its Cox representation. I think of it as a complex reflection group, like acting by the same matrices in 2-dimensional complex space. And one possible choice of fundamental invariance in this case is written here: x squared plus y squared and x squared times y squared. An equally reasonable choice would be to replace the second invariant with x to the 4th plus y to the 4th, if you like, but the degree is still 4. So I've listed here a table of what all the fixed spaces are, and the exponents of the group in this case are here. I obtained them by subtracting 1 from the degrees of the fundamental invariance. So it's 1, which is 2 minus 1, and then 3, which is 4 minus 1. In this group, besides the identity, which has fixed space 2, which is why you only see 1 q squared appearing here, there are 4 different reflections, and so you get q to the 1st power 4 times, and then the 3 rotations, they only fix the 0 subspace, and that's where you get the constant 3. And indeed, in this case, you see that that the sum over the group factors into a product of linear factors involving the 2 exponents 1 and 3. So I'll come back to D8 again to illustrate our results involving the normal reflection subgroups. Let me now define what those are. So normal reflection subgroup of reflection group G is going to be a normal subgroup that is again a reflection group, as in it's generated by reflections. Here I would like to briefly comment that when we started working on this project together, we chatted with a few experts just to some early exchange of ideas, and to me, this is this notion of normal reflection subgroup is quite natural, but somehow if you know too much about this subject, it stops feeling quite as natural. Quite a few times the reaction was, do you mean normal as in normal subgroup from like group theory? And yes, we do. Yeah, it's just a funny thing. So the first fact about what happens when you have a normal reflection subgroup sitting inside of a reflection group is that one can force a quotient to again be a reflection group, but now acting on the space of orbits, which in this situation happens to be again a vector space. This fact had already been proved by Bessis, Bonafé, and Rouquier in a bit more generality than what we show, and in our case, the arguments are a little bit more straightforward. So I couldn't resist trying to include a summary of the proof goes. So it's possible to choose fundamental n invariants whose C-span is not stabilized by G, but there is a choice of them where G really does act on the span of the n invariants. And the trivial but essential observation is that I can compute the G invariance by first taking n invariants and then taking H invariants of that. And so what happens then is that I can find the fundamental G invariants living as polynomials in the n invariants, and now I have H is acting on this vector space, and the H invariants are generated by some polynomials that can't be algebraically dependent because they're equal to the G's which are not algebraically dependent. And so using the Shephard-Todd-Solomon characterization, that forces the quotient to be a reflection group. In fact, a little bit more is true. You see that this the span of an appropriate choice of the fundamental n invariants is graded by the degrees of these homogeneous polynomials. And so the reflection representation of H breaks up into graded pieces, and that makes it so that the H invariants can actually be chosen to only take in n invariants of the same degrees. And from staring at this composition, you notice this fact that the degrees of G can be obtained as products of n degrees of H degrees. That's part of one of our theorems. So up here, I'm just reminding you of the notation, and we have these two theorems. The first one relates the exponents of G and N acting on V to the exponents of G acting on E, and all the other numerological invariants that I can get from having three different reflection groups acting on in spaces. So these equations were actually discovered by my co-author Nathan Williams in an earlier work called Exponents, and he had found a case-by-case proof where he witnessed many instances of this kind of phenomenon, and now they're explained in a case-free way in general. Below that, you see we have our generalization of the Shephard-Todd-Solomon formula, but now involving the additional combinatorial data of the complex reflection group. And so I would like to briefly convince you that this is indeed a generalization. I mean, it has roughly the same shape, but in fact, it can recover the Shephard-Todd-Solomon formula for the three reflection groups that appear here. So For G, you get it by specializing to t is equal to 1. You see that on the left-hand side, the t disappears, and you're left exactly with the same sum occurring on the standard Shephard-Todd-Solomon theorem. But on the right, what happens is that you get Q. You end up adding the v exponents of n and the e exponents of g to get the exponents of g that you're supposed to have in the Shephard-Todd-Solomon. So in the interest of time, I don't want to dwell too much in the other cases, but you get something similar happening involving these numerological formulas above do let you recover Shephard-Todd-Solomon for the 3 reflection groups that I have here. So going back to the dihedral group, one can find all these numbers, the degrees and exponents by hand. We had already found the degrees and exponents for the full dihedral group. In this case, there are exactly 2 non-trivial and proper normal reflection subgroups. And the invariants for the different groups look a little different, but the numbers in this case actually don't change. The degrees of any one of these choices of n are 2 and 2, and so the exponents are 1 and 1. And in both cases, so in this case, it's not possible to choose the wrong version of this E star space, and one can obtain all these numbers again by hand by just staring at these polynomials and seeing how these 8 different matrices act. And you don't have to memorize all the numbers that I've written down. I just wanted to use them to illustrate what our theorem says in this example, which is that indeed you get the exponents of g by adding the ones for n and the exponents of g, and so on and so forth. And you also get to witness the our factorization, which in some sense slows down the Shephard-Todd-Solomon formula by doing things for n first, and then for g. And this is again just repeating what happens when you specialize in different ways or apply this differential operator to obtain the 3 versions of Shephard-Todd-Solomon for g, n, and h. So I believe I'm out of time, so I'm going to skip. We generalize this to have a result involving some Galois twists that a referee very wisely suggested that we try not to mention. So I try not to mention them, but here we are. And then I had some words about the proof, which if you're interested, please ask me in the questions. I think I'll stop here. Thank you very much.
Great. Let's all thank Carlos for the great talk. And now, Olia, would you like to do the questions?
Yeah, so the first question is from Alejandro. Do you want to unmute yourself?
Thank you, Carlos. Thank you. Great talk. I was wondering if you have also results for like when you look at the co-exponents and you instead of the exponents.
Yes, indeed. So the part that I skipped involving the Galois twist, I can get the co-exponents as the exponents corresponding to the Galois twist given by complex conjugation, because in this case you get the Galois twist being the dual, and so its exponents are indeed the co-exponents, and are both the Orlik-Solomon theorem and our generalization of that involving Galois twist generalizes to involve the co-exponents as well.
The next question is from Jia Yuan Wang. Would you like to unmute yourself? Okay, so he doesn't have a microphone. So can you tell a priori what R is given G and N?
No, not really. So this is something that I actually learned about recently. So somehow when you talk about reflection groups, either in complex or real land, this is a theory about concrete, like the actual physical subgroup sitting inside of GLV, rather than the group up to isomorphism or something. So as a small example, if you think about the cyclic group of order 6, can also be thought of as C2 cross C3. So the same group acts as a reflection group in two-dimensional space, but also as C6 in one-dimensional space. So the R might change a little bit depending on what you're doing.
Okay. And the second question is there a normal subgroup?
I'm very sorry, I had some technical issue and I couldn't hear the question. Could you please repeat it?
Is there a normal subgroup zeta function for complex reflection groups?
Gosh, I had no idea. Maybe Nathan knows or Theo. Theo has been great help at it with this too.
Okay. So question from Yuval, what about counting normal reflection subgroups of affine wall groups?
I also don't know. There should be something that one can do, because you know, when you sit down and try to figure out how to get a normal reflection groups, you know, pick a few orbits of hyperplanes, and then for each one some subgroup of the cyclic fixer for that hyperplane. And my understanding is that these other things can be counted as well. But I'm sorry to say I have no idea.
Okay, and next question is from Vic Reiner. Would you like to ask your questions?
Sure. The quick one, Carlos, is do Bassis, Bonifay, and Ruquier, do they give us any classification of the normal reflection subgroups?
Yes, but so what they actually work with, they're more interested in when is the quotient G mod n a reflection group on the tangent space to the quotient V mod n, and what they find is that happens if they have several different characterizations, and one of them is that n is generated by reflections and what they call double reflections, which are things that fix a codimension 2 thing instead. And in the context of the questions that they're interested in asking and answering, they're interested in the case where there are no reflections in the normal subgroup at all, because they somehow get to reduce to the situation that eliminates every single situation that we're interested in. But they do have a classification for all the normal subgroups that are now generated by double reflections, where they've kind of ahead of time gotten rid of the reflection part.
Yeah, thanks. I'll skip my second question, which is in the chat.
Okay.
Great.